robot arm, we had gravity involved. Do we need to involve gravity here? This is a 2D motion, right? Depending on what your car does. If you're jumping over hills, yes. If it's a rad car, if it's just a car that you drive on the streets of Columbus, no, right? There's no change of gravity that impacts your motion. Unless you're doing the hill climbs and down, then that's a different case. So we are solving for a general case of you driving on a straight line. Not much change of incline, right? That in the span of the length, it does not impact our motion, our dynamics. So I expect to see something theta double dot, something theta dot, because I have two velocities because I have two differential wheels, right? And then some torques. The wheel have torques, right? You have to rotate them. That's how you control them. So this is this is the dynamic I expect to get. Now we have to write it. We have to drive that. Looking at the really beautiful image there, these two wheels are how the robot moves. So, you know, if both of them move forward in the same direction, the car goes straight. If one moves the other direction, the car starts rotating, right? Then turn right, then turn left. That's how we can control them. Now, there is a fixed axis reference frame for this case, which you can put it anywhere you want. In this example, we are putting it here. So meaning that the zero of this environment, we decided to be here. The zero of the environment could have been the place that the car initiates moving. That's up to you. But you have to have an axis on the car, right? That it moves with the car. Now, if you want to see, so this has how many degrees of freedom? 3. So 3, X, Y, and then you're rotating, right? The heading is called heading. So X, Y position is where the car lands. The heading is how far the front of the car, if you have the vector coming out of it, what's the angle between that and where you started moving from? How much? I'm here, and then I'm moving. Angle that I'm creating, this is your heading. You usually control the heading angle when you have a 2D motion. So that becomes important. That's why we have a vector here. We are showing that the velocity is going to be in this direction, a straight velocity. Our linear velocity is going to be in this direction, in the middle of the car. So I can say there is some distance, B equal, so center of the mass of the car. And I know that there is a radius for every wheel, right? I'm just trying to identify, let's say, the kinematic of my car, the specification of the car itself. And you have the center of gravity and center of mass. The other thing that we can say about this is each of these wheels, they have a velocity, right? Angular velocity. It can increase, but you have the control over that velocity. Right and left are separate. So we are going to treat them as separate. So I'm going to say this velocity here will be r theta dot phi dot L left wheel r theta phi, sorry, dot r, this is right leg. So this is my right wheel. So right wheel, left wheel. So I identified what kind of velocities I have, what's the direction of my velocity, and I know if I'm moving around the reference frame of the body frame moves. This one is Y, with the car. My fixed frame stays here, if that's where I started my fixed frame. We can write r phi dot r is going to be our linear velocity the car is going plus some b times omega. B is the distance from the center of the mass, and then your omega is the angular velocity of your wheel. And I can write r times, so basically the velocity of the wheel on the left side is going to be v minus b omega. If I'm turning, one is going to be deducted, one is going to be added, right? Now, the position of the car or the state P that we're going to consider, because we have 3 degrees of freedom, we have x, y, and theta, which is the heading here. Usually theta is shown by psi or phi, but here theta is the deviation that you have from the straight line that you started, right? This is your theta. Now, if P position is x, y, and theta, what's velocity? What's P dot? Yes. So x dot and y dot are your linear velocity because of the linear position change, and theta dot is because of the rotation, right? Angular velocity. So I can write v cosine of theta, v sine of theta, and some omega. This is my angular velocity of the wheel. This is our linear velocity component. The wheel rotates, right? It has some omega. Could be variable, it could be constant, but we're treating it as a variable. Now, okay, cool. I know how to represent my position. I know how to represent my velocity. Now, we want to see if we can write the equation of motion. If you remember, when we were dealing with the manipulator, we used fancy way of writing the dynamic equation. Here, we're just going to use Newton and mv dot equal to all the forces, and then I omega equal to all the momentums. We're going to use that Newton-Euler equations. So I'm going to say there are going to be some tau L and some tau R, right and left wing torque, wheel torque. And mv dot is going to be 1 over r tau of r, which is the right wing, plus 1 over the radius tau of the left one. That's for linear velocity. For the angular velocity component, I omega is going to be b over r tau r plus minus b over r tau l. All right, because they can spin against each other. Now, I is the moment of inertia and at the center of the mass, and m is total mass that we are applying at the center of the mass, right? So we have two kind of velocities, linear and angular. They are going to create two kind of motion for us, linear motion and angular motion. So we are writing a general equation again. We are writing a general equation for this motion. Agree so far? That makes sense? Like, now, we can put this in matrix form. We have two velocity components, so it would be nice if we could write one equation that represents both of them. So I can put these into matrix form. All I'm doing is rearranging. Nothing new will be done after here. We are done. There are two equations you can use. So we're going to play a little bit with it and bring it to the form that we are familiar with, which is a second order differential equation. So I can write V and omega are, you have to do a little bit of calculation to get to this. R over 2b negative R over 2b, B dot R, B dot L. This comes from here, okay? And then, what happened? Okay, I need to add a page here. I ran out of space. Add a page, okay. Great. So I can keep writing it here. Then
I can say that, all right, I have my V, then I can write my V dot and omega dot as well. So it's not W dot, it's omega dot. I can get that from here, right? It's not omega dot, it's just omega. So if I put that 2 stars, then I can follow from 2 stars. You can put that in matrix form, 1 over MR, BI times R, 1 over MR, negative B over IR. So that is radius, that is inertia, times tau R, tau L. All right, so if you remember from the second order differential equation, we usually have our general torques and force on one side, everything else on the other side. So I'm going to use this. I'm going to say, okay, if I keep tau R and tau L on one side, what do I need to do? The inverse of this matrix pre-multiplied by the vector on the other side, correct? So I'm going to do that. This, copy, paste. I'm going to put inverse so you can see the difference. Inverse, V dot, omega. Bless you. All right. Omega dots. So I have my V and omega from here. I'm just gonna get the differential partial, sorry, the time derivative of that. So time derivative of that will give me this guy times R over 2, R over 2B, negative R over 2B. And then now I have P dot R, P double dot R, and P double dot L. Cool. I have a matrix here. I'm going to call it M, and I created theta double R, like a phi double dot, which is coming from the velocity of each wheel, right? That's what we can control. We can control the velocity of the wheel, and that's how we control the position of the car. So I created tau equal to some matrix M, so tau R and L equal to some matrix M times P double dot for right and left. So that is only if I have a linear system that doesn't have any friction, anything. And what if I wanted to see what is the connection between right wheel and the left wheel, how they impact each other, meaning that if one goes to the right, the other one goes to the left, what is the interaction between them? So since I know how the differential equation looks like, I know I'm missing a term that has a theta dot in it, right? P dot in it. So we can, so I'm not going into too much of detail into that, but you can model then because you have to then look at the wheel itself, but it would be a term of some matrix B multiplied by your phi dot, and this is going to be some fixed value BR of right wheel, characterization of the right wheel, times the velocity of that, minus some characterization of the left wheel, times the velocity of that. So knowing this and this, we can say M P double dot plus some B P dot is tau.
This is because of the dynamic of the wheel, how it moves. This is how the two will interact, and this is the torque applied to the second order differential equation. We know that
we know how the solution looks like, right? So we know if we wanted to control the velocity, how the response should look like. Now, when you have a system like a car that's very complicated, you have different ways of modeling it. One way is estimating, try and error, and try to tune those values for your model. Rather, like instead of modeling the exact car, the benefit of modeling with like some like experiment and then try and error is that then if your car changed a little bit, if the designer wanted to change a little bit of the car, you have to do everything again. But if you did run a test and try to estimate these values, you can run those tests on the car and find new values. Does that make sense? So until you have the model, the finals model of the car, you can use this method to estimate what does the dynamic look like. And once you have that, you can put it on software, CAD softwares, and it gives you all the moment of inertia, center of mass, and everything, and you can actually model it properly. All right. But to get to that part, for our goals, we don't need to do that because we are seeing the car as a point mass, so it really doesn't matter, right? Okay, so now when the important part when we are discussing about the motion of a car is that we know if we ask a car to, if you tell the car go forward, if you've driven your car and take your hands off, and even if you're in cruise control, what's going to happen after, let's say, happen one? Right? It's going to go right, left. It's not going to stay on the line. So there's always error. So we're going to model this error for position estimation. So now, when you are taking your hands off, your car is in autonomous mode for 10 seconds, right? And then you put back your hands and then correct the direction. When we are controlling and we want to design an autonomous system, we want our controller to do that for us. Estimate the position and bring the car back, change the heading. So all you do is controlling the heading, that's theta, right? Knowing where your final position is going to be. Now, we need to estimate a function and model for this error. We can divide this into, okay, if we define a car as a function, it has 3 degrees of freedom, x, y, and theta, right? And there are two other components, the right wheel and left wheel velocity, or change. If you think about a wheel, it's circle, right? So when it moves, there's a theta that's changing in there, right? Which one? So theta 1, theta 2. So here, not to get it confused with the actual direction heading of the car, we're going to call it SR and SL. So delta SR and delta SL are travel distance for the right and left wheel. If you have the diameter and you know the angle, you know how much travel, right? Circumference and then how much theta, how many rounds you bend. So those two also come into our states. Now our function has 5 states, even though we have to be with them, because we are looking at 5 different things here. Now we can define that as, okay, my car starts with a position that I'm certain where it is. 0, 0, 0, I said so. We're going to start from 0, 0, 0. And I'm going to say that at every time interval, there's going to be a change of delta x, delta y, delta theta, plus there are 2 deltas, there are 2 more changes, which is for the wheel itself, right? So we are kind of breaking them down. But now, delta S and delta R are kind of contributing to the position and the heading. So for the estimation, you start from, okay, think of an initial position and a change in the position. Initial position, when we start from 0, we know where it is. Or when we know where the, like we get a GPS point, X, Y, and then our theta is 0 because there's no heading. Our job is to estimate this as close as possible to reality. This is our true ground. This is what we're estimating. Now, a couple of the definitions of delta x is what delta y and delta theta is. They all are, we're relating them to the wheels. The reason is that if we want to control a position, we have to control the wheel travel. All right. And delta S is basically the average of right wheel and left wheel travel. Now to get the update, our P prime or the next position is your P position plus so this matrix is basically using previous slide just plug in all the values. So we wrote everything in terms of delta theta and delta S right now.
So if we want to get a basic equation for odometry position update, we're gonna have this. Our update position is going to be our current position plus this. That you can see right now is depending on delta SR, delta SL, and theta. And V is the distance of each group to the center of mass. Right? So everything is back to the car itself. Now, before we get into, okay, so we define a function, and before we get into how to solve that, we need to talk about error model a little bit. So for odometry, we usually have very rough estimates. So if we are not using GPS, if you're not correcting, we always have an error, right? So even your best estimate is going to be rough estimate, because when you're using a model, you're not assuming any friction, any wheel slippage, any interaction between wheel and environment or wheel with the car itself. So you're forgetting everything. You're just looking at your model. So you're gonna have an error. So your best estimate is not going to be very accurate. Now, if we can create that model and drives that error to zero or minimize it, then we will be close to reality. All right. Now we're gonna define a covariance matrix to show that changes the uncertainty of our input and output, uncertainty of the error. We need to know the probability of how much this error estimate is correct. We have to have the knowledge of that. All right. So we will assume that our starting position the covariance, initial covariance matrix is known. What would be a very good known covariance matrix for the starting position? Zero. There's no error, right? We have the knowledge of that. So that's our first step. Then our next step is going to be our first estimate, which is the second data. And then we can calculate based on that. So our second will be the first step for the next round iteration, and then we go further. Now, for error propagation, if you have a system that you have a bunch of input and then you have a bunch of output, if you know the error propagation or like let's say the uncertainty of your input, what can you tell if you know that? So if this is the probability of the input or uncertainty, you see the covariance. What can you tell about your output if you know the function? If you know the system, remember input, system, output. If we know our system and if we know our input, what we can tell about the output? Can we have a good estimation of the covariances from our output, and how? Think of control. Think of linear systems. If you have a linear system, the box we know is linear. We have some input into that. What do we know about the output? There will be, depending on what is happening in the system, it's linear, right? There will be convolution of all of those applied to the system. Now, look at our function. Obviously, it's not linear, right? Linear is different from a line, but this is not linear. Like, let's say we are assuming our function is not linear. What can we do? Like, we have a very powerful tool. If the system was linear, and we knew our uncertainty of our input, we would know the uncertainty of that. Now our function is not linear. What can we do? Approximate how? What kind of approximation? Taylor. Yes, Taylor Swift. No, Taylor Swift. So you remember we talked about if you have a nonlinear function like the pendulum sine of theta, you can find operating point around one point. You can linearize it and you can move to the next one, right? So we're going to use that. So if the system is nonlinear, we are going to linearize it, approximate it using the Taylor series, maybe the first sentence, the first part of it, and say that, okay, first sentence plus high order, you're going to scratch that and just with this one. So at operating point, you're assuming that it's going to be linear. Then, if we know this, we definitely know this, right? So our error estimating model is estimated. I want you to understand that. Okay? Okay, back to our, so knowing that, then we can use error propagation law. So the covariance matrix representing of propagated uncertainties will be equal to sum fx, which is hello, a Jacobian matrix, times cx, which is the covariance of the inputs, that we already know what it is, multiplied by the transpose of Jacobian. Now tell me what was Jacobian. It's a mapping, right? So it could, you remember I said it could be different, we use it in different places. So Jacobian is a mapping that tells you the relation of input and output based on what? Differentiates over the states that are important, right? How the system is changing. You identify those states as like, okay, these are my input. I'm gonna look, how does this one input changes, which is if I change X? How does this change if I change Y? So you are showing the easiest way to talk about changes is just getting the partial differential. And that is your Jacobian. So we are going to always identify a Jacobian function and use this error law. All right. So we have our error propagation law. The rest of it is basically I'm plugging in all the values in it, but defining a, so the next thing is that we have to define a covariance for input, right? Because we said we know the input covariance. Now, this one you kind of again defining estimating. We're gonna make our life easy. We are gonna say that this is an increment motion, is slow enough that we can say the right and left wheel are independent on of each other, which they are. We are assuming that, controlling them separately, right? And we say that our covariance would be proportional to some value, some coefficient for right and left wheel, which is KR and KL over there. So this is your covariance matrix. You see it's 2 by 2. Off diagonals are 0, meaning that they're not related to each other. They're not correlated. On the diagonal, it is defined as KR, a fixed coefficient, times delta SR, distance travel. So direct relationship to that. Meaning that if I travel 0, my covariance is 0. If I travel 1 centimeter, covariance is lower than if I travel 10 centimeter. Basically like defining a linear thing, right? Making our life easy again. Now I have the covariance defined. I know that I'm gonna define a Jacobian matrix for the function, for my system function, and I'm done. That's all I need to do. So your estimation would be component of the motion, so defining Jacobian for the position and all that, plus if you have wheel slippage, like wheel sliding, you have to also consider that in the error. It will be these two components. So we're gonna have the covariance matrix P that would be that we constantly updating it. So when we are updating our position, we are updating our covariance as well, because everything has changed now. So the previous state becomes the current state. Now, knowing all of that, I'm going to show you all the equations for two-wheel differential wheel that they are not correlated, they are controlled separately. So you're starting from here for position, and then this is for wheel slippage, delta LR. If you plug in, if you follow this, you'll see that we have this FP. This is giving us a 3 by 3 matrix. So that's for the first portion position. Then we will define similar thing for the slippage. This is going to be a 2 by 3, 3 by 2, 1, 2, 3, 3 by 2. A 3 by 2 matrix. And you basically plug these two in this equation. So you will have your sigma p prime, you have your covariance because of the estimate changes in it. Your first one, covariance is 0, and then you keep changing, you're calculating for every state, that will be your updated, and then next stage, this updated will be the previous state, and you keep going. Now, how would it look like? I put the code in today's lecture, so you can actually run the code and see how to code this.
It used to be homework, but, well, it's not anymore. So you will have so you basically, if you are moving along, let's say, the right direction, and you're not having any, error propagation, if you're not turning, if you're just trying to go straight, right? If you're trying to go straight, the uncertainty is that if I have little slippage or there's an environmental issue, I might go to right and left. So these circles are getting bigger, so they are the error propagation estimation. What does it mean? It means that a car can start from this position and go end up here. Another one can go so it says that it can be anywhere on the circle, right? Depending on how you define those KR and KL, because those are experimental to define. But you are defining a maximum circle, how far you're gonna get off track. If you're just going on a straight line, but it might have like interaction between the wheel and the road, things that you didn't consider. You did that. Now imagine if you're turning, so there is a turn involved. Then your error propagation becomes like this. Now you have a rotation involved as well, like this. Right? Again, this could mean that the circle that you're driving could be the inside circle, could be the outside circle, or anywhere on those points at any time, depending on how your controller really works, right? If it's smooth or not. But any of those points are probable. We're probably not gonna zigzag, but we're not gonna be going on a straight line. We're talking about the autonomous system. Easiest way when you're driving, get your hand off, like somewhere that there aren't car around you, drive for 15 seconds, see what happens, right? Basically this will happen because engaging one second or the other. If you have set your car recently, it will be like super nice. It will go straight for probably 15 seconds. If not, after 2 seconds, you're maybe right or left. Make sense? So there are 2 codes on the lecture. I highly suggest you running them. It basically creates these super. And we can change things in this, change KR and KL and see how it impacts these uncertainty circles. Right. So that was all about wheeled robots. That's all I would talk about. Now, if you wanted to design a PID controller for this, would there be something different? Not really. Like your PID controller takes the error, right? You define coefficients and plug it in. Same thing. It goes to the same second order differential equation. So you know the basic, your system and your environment, your dynamic is changing a little bit, but everything else you know should apply. All right, okay. That's it.